Hi, this is Alex from devstories.eu. OpenCV, Computer Vision Deep Dive, episode 18 of 20. The most impressive artificial intelligence deployments today are not running in massive, air-conditioned server farms. They are running on $2 silicon chips powered by a watch battery in the middle of nowhere. Moving complex neural networks onto these tiny devices requires a completely different approach, which brings us to AI on the edge, deploying to microcontrollers. Microcontrollers are incredibly constrained. We are talking about devices with kilobytes of RAM, a few megabytes of flash storage, and strict power limits. Standard computer vision models use 32-bit floating point numbers for their weights and activations. A typical model needs hundreds of megabytes just to load into memory. If you try to run that on a basic microcontroller, it will immediately crash from memory exhaustion. Think about a battery-powered, solar-recharged wildlife camera deployed deep in a forest. Its job is to spot an endangered snow leopard. If the camera wakes up its radio transmitter to send every motion-triggered photo to a cloud server for analysis, the battery will drain in a day. The device has to run the object detector locally. It must process the video feed directly on the silicon and only wake the power-hungry transmitter to send an alert when it specifically identifies the leopard. To fit a vision model onto a chip this small, you have to shrink it aggressively. You do this primarily through two techniques: pruning and quantization. Pruning is exactly what it sounds like. You analyze the trained neural network and remove the connections that have the least impact on the final prediction. You are essentially cutting the deadwood out of the network architecture so fewer calculations happen per frame. The second technique, quantization, is where the real size reduction happens. This is the part that matters. Quantization reduces the numerical precision of the model. Instead of storing every weight as a 32-bit float, you map those values to an 8-bit integer, commonly referred to as int8 conversion. The core trade-off here is straightforward. You are intentionally throwing away numerical precision. To do this correctly, you run a calibration dataset through the model to track the minimum and maximum values of the weights. You then scale that floating point range to fit exactly inside the 256 possible values of an 8-bit integer. This trades a tiny fraction of model accuracy for a massive reduction in memory footprint and execution time. An 8-bit model takes up exactly 1/4 of the storage of a 32-bit model. Furthermore, microcontrollers handle integer math much faster and with significantly less power than floating point math. Many low-power microcontrollers lack dedicated hardware for floating-point operations altogether. This means floating-point math has to be emulated in software, which is incredibly slow and drains the battery. With an aggressively quantized 8-bit model, when the wildlife camera captures an image, the neural network multiplies and adds small integer values in single hardware clock cycles. The microcontroller can evaluate the image in milliseconds, confirm there is no snow leopard, and instantly drop back into a deep sleep state to conserve power. The actual deployment process starts on a normal desktop machine. You train your model on a standard dataset. Once trained, you run a converter script that applies the pruning and 8-bit integer quantization. The output is usually a flat byte array, exported as a block of C header code containing the compressed weights. You compile this directly into your microcontroller firmware alongside your camera drivers. There is no operating system and no file system to load models from at runtime. It is pure compiled logic, executing directly on the bare metal. The ultimate constraint in this environment changes how you evaluate success. On a microcontroller, your primary metric is no longer peak precision. It is the number of accurate inferences you can execute per millijoule of battery power. If you want to help keep the show going, you can support us by searching for Dev Stories EU on Patreon. That's all for this one. Thanks for listening and keep building.